Hello, this is the third video in the series on the pairing heap data structure. It's a very good, very fast data structure to keep known of a minimum or maximum element that's been ranked. For example, very often used in priority queues, which of course are used everywhere, all over in computing. So let's review really quick where we are. We implemented add and meld, right? Add is the user interface for a pairing heap. We want to add a new ranking and piece of data. And to do that, what we really want to do implementation-wise is we want to create a meld feature and function so that in the future here, what we're about to work on is removing the top of a heap, right? So we add it top of the heap. And on the right, we see some execution that we ended with. First, let's start creating some a random list, a random heap of the numbers 0 through 9. All right, so random heap, and this will be useful because we need a bigger heap and a little more complex heap when we're about to implement remove. So, how are we going to do this? All right, so let's give us this display. Let's give us a blank line, and that's lovely. And then we need to build a, let's call it a random heap. All right. So how are we going to do this? We're, of course, going to use our very famous friend fold. And how are we going to do this? We, of course, need a function, as we always do. And we start with something, so what should we start with? Well, of course, we'll start with an empty heap, heap new, and then we need some random numbers. So we're going to shuffle up the range up to 10. All right, so we format this. So great, so as we recall, what do we get here? We get a number, right? Let's just call it rand_num. And then we get our heap. And we need to add this we need to add a ranking and data. Here we're going to have the ranking and data be the same, right? It'll be our random number, and we're going to add it into the heap. So heap add rand_num into our heap. So this should give us a random heap. And now let's print it out. Right, but let's use Racket's pretty printer. So first, pretty print. Let's set some columns. Right, let's have a max column of, let's say, 32, because we want to see the depth, any depth in our tree. Right, we don't want branches to go too far along the horizontal. We want to see the tree structure the best way we can. And now we'll pretty print our random heap. All right, so let's see if I've done this correctly. And we run it, and I didn't do it correctly, so excellent, fantastic. Right, so let's see what I did. What did I do wrong? We're adding into the heap the random number twice, and then the heap. It says it has no clause, so what is the problem here? We're going to spend the time to figure this out. No match for our something that looks like we're missing a pairing. This looks like a child, okay? And so where's our problem? So we're about the only function we're calling is into add, so we'll go back up to our add, right? Ranking and data, we're going to meld some heaps. We get our heaps, we do our, so what could possibly be wrong here? All right. This is good. Shuffle range, fold into our random heap. Add ranking and heap. There's no matching clause in meld for empty. Of course, duh. When we start with an empty heap, right, eventually it gets called into meld, so let's go up here. We have our ranking and data, which was the random number twice, and then our initial heap is empty, so we need to check an initial heap, and of course, none of these matches. So we're going to have to check a condition, right, that if we have if heap 1 is empty, we want to return heap 2. That makes sense, and we should probably go the other way. In other words, if we're given empty heaps, we want to return the other heap in meld. Totally makes sense, right? Excellent. And we need an else. The else condition is when they're both real heaps. So now we need to figure this out. Here's our close, and then here's our close for our cond. Save this. Let's give it a shot. Forgot to check. Great. So now we have a random. We can build a random heap, and it displays it. So in this heap, it looks like it started with a 5, and then 3 came in, right? And 3 became the head, and so 5 was his child, and then 4 came in, right? And or 0 came in, and then 4 came in, 8 all the way. All right, let's run another one. Right? We can somewhat divine the input into this, right? So you can see basically once we exit the hierarchy, having any hierarchy, that's when 0 appeared right before, right? So 0 didn't appear yet. So what came in first? Well, let's say probably 5 or 6 came in. We can't tell really which way, right? If 5 came in and then 6, then 6 is a child. If 6 came in and then 5, then 5 is still the parent, right? Then 1 came in, right? It became the parent. And then 3 came in, so it added to a child. And then 0 came in, right? Perfect. And then 7, 2, and so on, right? So we have a little bit of hierarchy, and perfect. So why are we here? We're here to remove that top element. We want to get the element, the data that has the lowest ranking. This is a min heap, all right? So what is our function? Our function here is, as usual, define heap remove, and we are given a heap. And how do we remove from it? Actually, this we need to match up. We need to do a match. And what does a heap look like? A heap is a list. In the list is the pair, so the ranking and the data, and the child. The children are after that. In our match, this needs to be surrounded because we only have one argument. And then, of course, what do we want to do, right? Well, we're throwing out the top. Here we're not returning it, we're removing it, right? We'll implement getting the top of the heap later. It's also very trivial. And so what we need to do is we need to get rid of that top, but then we need to figure out from the children what is the next top of heap. And for this, we're going to call another function called heap merge. Okay? And what are we going to merge? We're merging the children. Okay? So perfect. We're merging the children here. Now we don't have a merge yet. And as we can see, we don't even use all of the information. Do we really need the heap? Right? Not really. Do we need the ranking and the data? Nope, we only need the children. So now we need to define our heap merging. Heap, merge, and what does it take? It takes a bunch of heaps. It's merging heaps together to figure out, somehow, it's merging them together, putting them together, find the next single heap. It's building a heap, and at the top of that heap had better be the smallest, the next minimum item. So how might we want to do this? Well, because this is going to be recursive, as is always the case, of course, when in a functional language, let's start getting our match going, and in our heap, I don't want this variable, and in our match, what do we have? Well, our first match, unsurprisingly, is if it's an empty heap, we return an empty heap. And if there's only one child, if there's only one heap to merge, right, let's just, return it, right? If you got one heap, there's nothing to do. That is the top of the heap, right? Okay, great. So the real case is when we have two heaps and two or more. Okay, so perfect. So now what are we going to do? Well, when we have two or more, we already have a function, so we certainly are going to meld the two. Right? We're going to heap meld them, because that's going to figure out what, it's going to put them together and which one of those is the top. And then, as we tend to do in recursive functions, we're going to heap merge the remaining. Heap merge more, right? So, for having a bit fewer, just messing around, sorry about that, overlapping on my screen. Clean this up. Okay, so we need to meld two of them together. We need to build a heap out of it, and then we want to do that again for the rest of the elements. So that's great, right? And what does this return? It returns a heap, and presumably at the end, as usual, like everything, heap merge returns a heap. So what do we want to do when we have two heaps? Classically, right? We meld them. And of course it's called heap meld. So we are walking the list a pair at a time and melding those, chunk, 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 chunk. And then, because this is a recursive function, on the unwind step, we're melding those results back up. All right? This is a pretty cool auto balancing data structure. And of course, at the end of meld, what is the result? Another heap. So at the end of this function, we will have figured out what should be at the top of our heap. All right? So let's see if this runs at all even. We're running it. Didn't seem to break. Everything here was flat. Right? So it looks like 0 came in first. Let's do it again. Looks like 1 came in, right? And then a bunch of numbers came in the bottom up order, 6, 3, 7, 2, and so on, and then 0 came in. All right, we'll run another one just to get some hierarchy. Perfect, we got a little bit of hierarchy. Okay, so now that we have that, we should pretty print out. Let's remove. See if this works. See if I can spell pretty print. Heap remove of random heap. So we'll run it, and let's see what we get. So it didn't crash, and 0 was at the top, and 1 was at the top, so perfect. Seems like this particular execution works. So now let's look at the structure, and let's walk through the algorithm. And we're going to do this a couple times because it's pretty complex, and I don't have graphic and charts, which would be actually very helpful. So, so great. I'm going to tone down my mic's input. Sorry about that. I hope it wasn't too loud this whole time. Okay. So what did we start with? It looks like we started with down here at the very bottom, right? We started with 3 or 2, right? So let's just assume we started with 3. With 3, in came 5, in came 8. So that's how we get this. Then 2 came in, so now 3 is a child of that. Then came in 6 and 7, all right? Then 0 came in, so the 2 heap became a child under that, and then 9, 4, 1. Okay, so now we need to drop this off. So we do our pairwise melding and then unwinding of melds. So first melding is 1 and 4. All right, and we know 1 is eventually going to be it, so it's going to be the top. So 4 is going to be a child. Immediately we can tell. And notice 4 is a child by itself under 1. Then we meld 9 and 2, and of course 9 becomes a child under 2, so it would become at the same level as 7. So we have 2, 9 gets added as it does here, then we have 7, 6, and 3, 8, and 5. Perfect. All right, and 1 ended up being our, right, once our 2 got melded with the 1 and 4, 2 became the first child under 1, with 4 being the second child, and 1 is our top. All right, so let's try this again. Top of the heap, not going to go over how it was built. Top of the heap is 0. We have 4 children. Okay, so we're going to have 2 sets of melds together. First we meld 2 and 5, then we meld 1 and 7, right? 1 and 7, so 7 had better be in there. Yep. So 7 initially gets added to 3. It's at the same level of 3, 4, and on. Then, right, we know 1 is going to be the new top. So on the unwind, 2 gets added as the next, as the first, gets added last, and becomes the first because this is lists and we cons. It becomes the first element in the children. All right, let's do another one. Oh, this one's nice and deep. Good. Let's see what happens here. So our top is 0, and then we have a bunch of children, 5, 6, 1, and so on. And then 4 has some hierarchy, right? 4 has 2 children of that. So now, how many do we have? We've got 2, 4, 6, 7, 6, and then a leftover. So this is the case where we have a leftover. Okay, so 5 and 6 get together. So we should be seeing 5 and 6 together in our result, and we do. 1 and 2 get put together, so 2 becomes the child in 1. Okay, that's good. We know that 1 is going to be the new top, so 2 had better be a child by itself, and it is. Okay. 3 and 7 get merged, right? So that's perfect. 3 and 7 get merged, and then 4 is returned on its own. And 3 and 7, here is 7 being a child on its own under 3. In the unwind step, this 3 and 7, 4 gets added, so 4 becomes a child of 3, and that's what we see, and all of the hierarchy of 4, right? And then this 3 gets added to the 2 and 1, so that's why it's before the 2, and then the 5 gets added before that, and the 1 is the top. Okay, so I think we're done. I think we've implemented remove, which is the particularly important part of the algorithm of keeping a pairing heap as not balanced, but somewhat balancing, auto-balancing a bit, having some depth to it so that it ends up with the performances of the classic log performances we get out of trees. Right? Otherwise, adding is very easy. We just do this meld. But once we remove the top, because that's the only element we really have access to in a heap is the top, we then need to merge all of the subheaps, and we do that through pairwise melding, and that's why this is called a pairing heap. So I hope that explains the root, the key part of this data structure. We'll have one more video on this where we just get the top, and we'll run some more tests. Okay, so I think we're done. Talk to you later. Bye.